Well, hello and welcome to episode 4, podcast 4 of the MotorDoc Energy and Emissions Reliability and Maintenance podcast, or whatever we call it this week. In any case, this week we're going to discuss MEASUR. Now, MEASUR is a U.S. Department of Energy tool. Now, up to now, I've basically identified the concept of tying your maintenance and reliability goals into energy and emissions if your company has an emissions goal in order to get more exposure. I'm going to be actually talking on this again in 2 weeks at the 2023 Society for Maintenance and Reliability Professionals. But in our last episode, I discussed how to use EMPATH Electrical Signature Analysis to identify individual defects. Now we're going to get into how to use an overall tool, or a calculator, I should say, because next week we'll discuss the overall tool called Verify, that you can then use to tie everything together. And between all of these tools, you will be able to directly tie, not correlate, not estimate, but actually tie real numbers back to your program. Does this have an impact? Well, there are goals in place, and we'll discuss those under the FEMP program, where they have already set world class based upon energy costs per foot. So there's all kinds of goals and KPI goals we can set based upon our type of industry and based upon our type of facility that exists, that's already established, meaning we don't have to go in search of a benchmark. These are also recognized by AEE, or the American Energy Efficiency Group. But anyways, let's go ahead and take a quick look at MEASUR. Now, last week I talked about electric motors. So we're going to stay with the motor stuff. And as you can see in here, there's pumps, compressed air, process heating, fans, steam, treasure hunt, which is how to go out and find opportunities, which, go figure, are primarily maintenance opportunities. Wastewater, so waste treatment. Electric motors, including an inventory, a pump inventory, and then this here, data exploration. This is a series of calculators where we can go in and just identify individual things. So if I don't have an ESA tool available, or I want to justify an empath, of course, I can use this tool. So we're going to start out by taking a quick look at some calculators. And as we move forward later on, we will begin to discuss some of these other calculators and so on. So pre-assessment screening means these are things to go in and take a look at your overall facility's status. It's actually a scorecard. Unit converters, mostly you'll hear me talking in terms of kilowatts, but as we move forward later, I'll probably use something along the lines of therms or British thermal units. Those are two different measures. Combined heat and power calculations, that would be basically generating your own power while also producing steam. Cash flow. So simple payback sucks. And if you're using simple payback to address any opportunity, you're cutting yourself and your company short. Often we see hurdle rates, say a hurdle rate is even at, say, as high as 20%. We'll see hurdle rates of 20%, meaning that's the point where the company says the value of money now against the future makes sense. And they would take any projects that exceed 20%. Is often a 5-year simple payback. So later down the road, we're going to start talking about how to take some of our opportunities and present them in such a way that we can discuss the financial part. For those that are, electrical and mechanical engineers, this is an industrial engineering arena, or reliability engineering, which is a subset of industrial. Power factor correction, how to properly size capacitors. Here we go. Here's the savings that I talked about, how to calculate it. We'll come back to this later. How to identify energy savings through reducing electrical usage. Basically what we've been talking about. So you're going to see simple calculators to do what I was talking about. Weather bins, basically how to tie your costs back to weather. When we discuss how to take a look at what savings really are, we have to be able to tie back sun days, not weekend Sundays, sun days, cooling days, heating days, cloud days, a whole lot of other things that have to be considered. Yeah, it is that complicated. I mean, there's whole certifications around that. There's work around that. It took me a long time to go through that when I ran the Energy Resources Center. So all of this here is important. I did miss this part here, altitude correction. So some of these are brand new. I mean, this is the latest update. I haven't seen some of these yet. So we will return to those another time. Compressed air. Okay, so if you're out there using air leak detection with ultrasound, they have their own calculators, not always particularly correct, but this will help tie that stuff all back in. It's there. It's done. It's a calculator. And it was developed not only by the Department of Energy, but at Oak Ridge National Labs, where the EMPATH comes from. Hence, it's really accurate. So as I go through, of course, there's all the stuff with compressed air systems, different types of values associated with that, fans, lighting. I mean, lighting is lighting. Well, we're going to cover some of that lighting aspect later, because there's been a lot of people we've run into that say, oh yeah, we put in our LED lighting and we didn't see any savings. Matter of fact, our costs went up, and we're going to discuss some of that as this podcast continues. Here's the ones we're interested in. The motor calculators, we're going to come back to that. Process cooling, all your chillers, cooling towers, everything else. This is relatively new. Process heating was always there. That's definitely a good one, especially if you have boilers and everything else. There's a couple of new calculators in here. And you can see there's a lot to cover. And then also pump calculators, steam calculators, again, a lot. Some of these are new. Wastewater calculators, that's a new one. So looks like a whole lot of stuff that I would have to learn. Well, you can probably pick it up and run with it. So let's take a look in the motor section. In the next few minutes, next few minutes, 1, 2, 3, 4, 5, 6, we're going to cover 6 items. And I'm going to show you how you can use this in order to make estimates of your load that are relatively accurate, look at your field efficiency, look at some of the things we talked about, like how do I get a quick measure? I only have a voltmeter and an ammeter. How can I go in and tell if I've made improvements? Well, if I know my power factor, which is usually on your motor control center, if you have relays, you can usually get that relatively easily. So you'll want to take a look at your power factor. Truly, it's supposed to be the motor power factor. And I've been watching some people's presentations lately, and they're equating system power factor as motor power factor. And look, all you have to do is this, and you can improve the motor efficiency. Absolutely false. Wrong, wrong, wrong. Those are two different types of power factor. Okay, I use power factor of the motor, which are the calculated losses inside the machine that will affect overall power factor, but the actual power factor of the machine, which cannot change unless I have damage to the machine, will affect its efficiency. So, but system power factor will not. Let me clarify that again. System power factor will not improve the efficiency of your motor. It will improve the effectiveness. It's going to reduce some losses that are system losses, not motor losses. losses. So with that, we're going to go ahead and move forward. So let's see, we're 10 minutes exactly in. So we will take a look at NEMA, the first calculated, NEMA energy efficiency. Okay, this looks complicated, doesn't it? So I come up and I say, okay, that's a 150 horsepower motor. For instance, you know what? Let's make this more common. Let's go with a 15 horsepower motor. The motor RPM, it's going to be a 1800, pretty common. So let's say 1780 off the nameplate. Okay, well, look at that. And if I want to, I can say, okay, it's a premium efficient, brand new efficient motor. Look at that. So a 15 horsepower, 1780 RPM motor, premium efficient, the nominal average efficiency is 92.5. That's right out of the manual, right? So let's change the speed. Let's call it 1790. I don't see anything. Well, that's because it's an 1800 RPM motor. So if I just know it's a 4-pole motor, I would type in 1800, and there I've got it. So that's it. If I made this a 50 horsepower motor, the nominal, meaning average efficiency at 1800 RPM, is going to be 94.7 as a premium efficient motor. What if it's a 50 hertz motor? Well, it changes it slightly, right? So I believe, did it? No, it did not. So complicated, really, really complicated. We'll talk about what efficiency looks like, but this is the full load, 100% load efficiency. So let's go back to our next calculators. Oh, should have just clicked on motors. Let's go to motor calculators. There we go. Motor performance, the curves. Okay, this must be complicated too. So here's my curves over here on the right, and this is going to be a table. And you notice I can copy the table. I can do certain things here on and off grid lines. I can make this as large as the page so I can view it. There's all these other functions up here. It's written in a specific language, but that's neither here. So here we go, 60 hertz. This will be nominal, meaning average across motors, if you don't have that available. So, and you notice this neat little thing down here, estimate full load amps. What if I don't have something and I say, I know it's 100 horsepower. Oh, yeah, I know it's 100 horsepower. I know it's a 4-pole motor. Well, let's say it's a 1780. Okay, and I know that we're going to stick with premium efficient because that goes under the last IESA. And we're going to say it's a 460 volt. Now, your power supply is probably 480. Your motor is going to be 460, and that's to allow for a voltage drop. So we'll put in 460. And let's say I see this. I'm not clear on what my nameplate amperage is, so I can click down here to my estimated current draw, and it's going to give me an estimate based on that size machine. Well, let's say I take a look at it. It's actually 120 amps. Let's watch over here. So you see, I now have a graph, and this is going to tell me based upon, you can see the bottom part here, down here, there's my load, percentage load, in a decimal point. I know it's not showing percentage. But up above, it's telling me my efficiency, the motor power factor, and my full load current, and what's happening as I reduce load. So if I want to come in and right size something, there I go. Okay, so that's it. And then I can copy this table here and do whatever else I want. I can turn on and off those grid lines. I prefer the grid lines for me. But in any case, yep, I come along here and I say, okay, click. There's a point. Let's get rid of that one because I made an extra. And I know it's also going to run at this point here. Just click inside there. And it starts building a table for me in different spots. Now I can use this for all kinds of things. And then I can take this, say if I know that I have 4 operating points, and I want to choose a motor size. Maybe I need to do, maybe it's a 75 horsepower application, and I've got to take a look at this, and I know that the load is going to be, the 100 horsepower motor, the load's actually going to be down closer to 75%, right? So we'll look at the bottom. There we are, 75%, and I select that point. And now there's all the stuff I need to know for that, including the efficiency. And then I say, okay, let's do another scenario. So I print this out and I set it up, and then I go in and I do another one at 75 horsepower. So it's 100% loaded, and then I can do a direct comparison. Now this gives me an idea of what I'm doing. Now it's not quite what we're doing so far, but I can start making some decisions based upon the motor systems. So let's go back to motors again. Percent load estimation. What's my load? Okay, and here we go. The average power factor, not of the motor this time, but the average power factor of the system, let's say is 78.78. Here, okay, it's in percentage. So let's say it's 78%, 0.78. And my motor is 477, 483. Yeah, you notice I'm putting in something that looks realistic. And then we'll just put in 472. Okay, so I have an obvious unbalance there. The motor, let's say its rated current is 115 amps. We'll go with that 100 horsepower. And the rated voltage is 460. Now what's it doing? Well, it's going to compensate for our power factor, voltage unbalance, and the resulting current unbalance. So let's say we are measuring, because this is going to be my medium and then high and then my low. So let's say we're measuring 79 amps, and then the next one is 88 amps, and the next one is 77 amps, just for fun. Well, you'll notice that as I changed each of that, I've got a 1% voltage unbalance, I got a deviation from average, I've got 73% load, I've got my input horsepower, or my input kilowatts, I should say, at 52.45 kilowatts. So if I'm estimating this, I can then go back to the machine and what have I actually measured there, et cetera, et cetera, et cetera. And then it's compensating for the average voltage and current. So this is my next step. If at any point I get confused or Howard didn't tell me enough stuff, I can click on help and it's going to give me an overview. Okay, so there we go. I'm sorry it's really complicated. People keep telling me this stuff is complicated. I keep going, not so much. So let's take a look. Next one is the coupling, whether it's a fan or belt or whatever else. I can say, okay, 8,760 is 24/7. I've always kind of used 6,000 hours. That's 3 shifts a day, 5 days a week, and 2 weeks off for vacation. You've got to send your motor to the Bahamas. They'll love it. And then what's my actual cost? Well, depending on where you are right now, this might be incredibly different. So we're going to use 12 cents. We're going to say the motor power is actually that 75. Well, it was 73, wasn't it? So let's go ahead and we'll take 73 horsepower equivalent. Our percentage, oh, that's motor horsepower. Sorry, my bad. 100 horsepower, I'm not paying attention, I know. And then 75% loaded, that's what it was. So here we go. Now it is running all of my consumption and my costs, comparing the belt drive to a synchronous belt drive. Okay, or I can say, okay, notched V-belt to direct drive. And then I can come over here and it's going to calculate all of the different opportunities that I'm looking for, right? So what's the original, what's the modified, what's the efficiency of that, and then what is the cost savings associated with it. Not too bad so far, right? Next one is repair versus replace. This is a common call that I get. You know, when do I repair versus replace? Well, be perfectly blunt, you know, you will usually make it, especially nowadays, you'll usually make it based on economics. So let's go back up and we're going to say this is that 6,000 hour machine. Let's say it's 50 horsepower motor. Oh, it updated it for me, didn't it? 100 horsepower motor at 75% loaded. Cost is 12 cents per year. Okay, back to where we were. Let's say it was a standard efficient motor before, which is going to be about 92%, versus the premium efficient motor over here. And yeah, I don't think so. The 100 horsepower motor is going to be somewhere to the tune of, say, $7,800. Okay, so we say $7,800. Cost of the rewind, let's say, is going to be, and by the way, you can do this if it's just bearings or any type of repair. It doesn't have to be a rewind. So let's say we're going in and we got El Cheapo down the street. And because we know it's El Cheapo down the street and he's not paying attention to his ESA requirements, we're going to say, because, oh, I saw this video on LinkedIn. Everybody was going, that's a great rewind. Oh boy, they're doing so great. And while we're watching, you know, somebody with a metal ball peen hammer the outside race of the bearings to get it on. So let's say it's a 5% loss. And that's being generous. So it's going to be a 5% efficiency loss. Well, where do I get 5%? Back in the 1990s, when all the new materials were coming out, pardon me a second. It's late evening, must have my coffee, and by the way, I'll throw in a quick save because this is one of my favorite cups from RDI. And yes, I use an RDI system as well. So but anyways, back in the day, BC Hydro in Canada, Ontario Hydro, and Hydro-Quebec all did a series of studies. Two were blind studies, and the Hydro-Quebec study involved an actual rewind process, both how you're supposed to do it and ways you shouldn't do it. I got to be on the advisory group for that, 1993. So we know that 5%, if somebody does a really crappy rewind or repair, that's what we're going to get. Now here's something fascinating, but with the newer motors, and this was a bone of contention back then, you know, they still report it as a 0.5 to 1% drop. There was a lot of fist fighting between ESA and DOE over that and everything else because really the research didn't support it. If there was a proper rewind, a proper repair, temperatures were controlled in particular, bearings were replaced properly, and everything else was done correctly, this value should be 0 reduction. Okay, so they put in 1% because they're estimating, because most people don't bother going down and looking in the repair shop anymore. I don't know why. Most repair shops would love to have their customers stop by and learn why they're different. So I go ahead, I put all this stuff in. It's a $4,500 repair. Basically, I come up here, energy consumption. The rewound motor, you notice existing. And then the new motor would actually have considerably less consumption per year in kilowatt hours per year. The energy cost is your basically your kilowatt peak. So whatever the kilowatts are actually at that load are actually there. So that's going to be my demand charge. So I add those together, and then I can take a look down here, and I say, okay, the energy cost there, this is the actual dollars. Oh, I'm sorry, I was wrong. Kilowatt hours, they didn't include the demand charge. This is without the demand charge. My apologies. I'm leaving that in because I've got to be fallible once in a while. Or more. But in any case, you can see here, the original one should have been about 43,780 or 43,800. After the repair, the annual running cost is going to be about 46. You notice that a repair versus replace decision actually involves the energy. So that makes that repair versus replace, which is a maintenance decision, not an energy decision, right? Would be to do that. So the total thing, it says simple payback of 4.28 years. Son of a gun. If I go with the new motor, it's going to take me 4 1/3 years to get paid back. But what is it really? And that's one of our future ones. So 4.28 years may be perfectly fine. You may want to go with the new motor because what is $1,800 cost now versus 5 years from now? So what is the real cost of that $1,800 if the company were to invest it in something else, right? So are they making money back? So here we go. Once we do that, and we say, okay, new motor is this. Here is where they start taking a look at the incremental savings. Sunk cost, $4,500. Annual energy savings, this. Cost difference is this. Energy cost savings is this. Simple payback is now a year. So I would say replacement makes a lot of sense. Okay, so if I repair it versus a new motor, or if I just go with replace versus rewind, I'm going to get two different numbers. What I really need to do is something more advanced. But that's neither here nor there, and we will cover that at another time. So that gives us a repair versus replace. Here we go. This is that one. We've already used this. And so far, if you're sticking with me, you're seeing that, we're kind of seeing the same thing. Because back here, percent load estimate, where I had the input power, I do all my calculations off of that input power, right? Not the losses and everything else at the end. This is the power that the system sees. The efficiency of the motor is the shaft power versus this power. I've had these discussions before, and it really depends on the goal of the person you're talking to. Oh yeah, improve the shaft horsepower. Okay, but what is my actual energy cost? Oh, but the shaft horsepower is good. What's the energy cost? So if you reduce the shaft horsepower, but you've done damage to the machine so that the input power goes up, you really haven't fixed anything. So when I use examples like that, it's something I've run into recently. So anyways, let's go to full load amps. Again, this will give us the ability to go in and say we're a 60 hertz machine, and the rated horsepower is, let's select 50 horsepower. For some reason, everybody's, in all these research projects has always been fixated with 50 horsepower. Well, 0 amps so far. So let's see, motor RPM at 50 horsepower. The nameplate RPM is going to be, in this case, let's do a 3600. So let's say 3550, and we're going to call it energy efficient. Infinite current. Oh my gosh. Well, I mean, we need some voltage, right? So let's say, and you notice over here on the right, it's giving us a range from a 200 volt motor up to a 15180. But we're just going to stick with, well, in this case, we'll say it's a 240 volt motor. So if I go 240 volt, connect the motor for 240 volt, 50 horsepower, the nameplate should be telling me about 107, 108 amps. If it's 460, then that's giving me about right don't have a nameplate well, I do have a nameplate in front of me, but we'll do that at another time when we start tying this all together. So overall, right now, just looking at just motors, we're not looking at the rest of the system, fans, pumps, and some of the other stuff that's in here, and even compressed air, if it's driven by a motor. All of this can be covered under the calculators. For the motor, we worry about the incoming kilowatts, and then that makes it relatively easy for us to do the other stuff. So let's take a look at one last thing, just to make a point. And we're going to come down here to CO2 savings. Now, the other day I said we were, let's see, so it's electricity. This is important. Zip code. So what it's going to do is it's going to set up the Egrid region. So if I leave it open, it'll try to pick a whatever. So you also notice that there's a thing over here, add modified, so this will allow us to set a baseline. So let's go ahead and we're going to say, take about where I am. So it's going to say this region, that's 484.3 kilograms. Now this is for my inventory, not reduction. So I'm going to put in a value, let's say my baseline is in megawatt hours. So let's say I'm a 3 megawatt plant, right? So that would be times 6, so 18,000. Okay? And that's going to tell me the number of tons CO2. Now that's metric tons, which is 2,240. So we're going to go ahead and modify this condition now. And we're going to say, okay, let's go ahead and oh, this is for different types of energy. So that's for a different fuel, sorry. And we're going to say our output here is going to be reduced to 17,900. Okay. And let's get rid of energy use 2. And you can see the modified reduction drops me down from 8717 to 8669. So that is a total reduction of 48.4 tons. So when I go in and I'm starting to track at the larger scale, or even if I say, you know what, let's go ahead and we're talking about that one machine. So we know what our emissions rate are specific to our Egrid region. And that motor's consumption, let's say we found a 5 kilowatt motor, or a 5 kilowatt loss on a bearing. And that's very realistic. So that's going to be 5 kilowatts times 6,000, right? So that's 30,000 kilowatt hours, or 30 megawatt hours. And I could also put in the total consumption of the machine off of the previous calculators if I don't have an empath. I could literally go in and say, okay, let's go even better. Let's say it's, I think we had 42.3 kilowatts, right, in the consumption of that one machine, and we times 6,000. That one would be 253.8, right? And then we come over here and we say, okay, we reduced it by 30. So 253.8 minus 30 gives me 223.8. Okay, This would be my measured value again, that I could calculate off the incoming power of the machine and just multiply it by the number of hours. And then that tells me that I've reduced, by replacing that bearing, 14.5 metric tons of CO2 per year, operating at 6,000 hours in my specific region. How's that for fun? I could say, let's go with okay, so a different region, and that's going to change that, and I'm still looking at roughly the same. Okay. Oh. Okay, or I have no idea if this is real. Let's see. Oh yeah, New York. Okay. New York region. And you can see much different than, you know, the Illinois region here. And then that reduces it to this. So if I go off actual, the grid region, then my savings changes a little bit. So I can use this and then tie it directly and say, hey, replacing that bearing, in addition to, and you've got all the other parts of the calculator, we also reduce 7.5 tons of CO2. Look, the Department of Energy and EPA say so. So with that, we're going to go ahead and conclude today. I know, I originally said 5 or 10 minutes for each of these, but I talk way too much, and this stuff is way too interesting for me. So in what we're going to end up doing is they're going to take what they take. But next week, when we cover that one, we're going to go through Verify. Now, Verify is a way for you to tie all of this into a program at the corporate level by facility, so you can actually have your facilities competing against each other for whose maintenance program is having the greatest impact. And with that, again, just a quick reminder, this is how I sell my programs. So other people have asked me, how is it when you're in, they can't shake you out? Well, it's because I actually tie the stuff of interest directly to the people who are interested at the top level. And you know, once you start doing that and you can show real numbers, it has a tendency to keep you there. So have a great week. I'm going to be in another state teaching a class to a group of predictive maintenance and maintenance folks, followed immediately by the SMRP conference. Enjoy. If you're there, come see me. We'll be doing. I'll be on the floor on Tuesday from 11 to noon in Innovation Lab 1. Thank you very much.